the integral from a to b, 0 is less than a is less than b, of 1 over x dx. According to the definition, if the Riemann sum f of xi times delta xi, Riemann sum from 1 to n, as the p modulo approaches 0, if the limit exists, then we say it is Riemann integrable, right? Denoted as integral from a to b, f of x dx. Partition here, delta xi partition inside interval ab, right? So here we have the partition. From a to b, right? That's my f of x here, perhaps like this. Right, here we have a partition. x0 a, x1 here, x2 there. All right, perhaps x3, and so on and so forth. So the p modulo, meaning the maximum here, any given partition, where you fix this partition, right? So what's the biggest small interval out of all the small intervals, right? Perhaps it's this one. What's its width? The width of the largest small interval is denoted as p modulo, right? As p modulo approaches 0, in other words, as the width, as my biggest small interval gets small enough, how about the other small intervals? Of course, they will be even smaller enough. So in that case, my partition is dense enough. So in this case, as my partition gets dense enough, if my Riemann sum, right? So the width of each small interval times the functional value, and the choice of xi is random, right? We can choose any xi inside this small interval, right? They multiply together, right? Then add them all up. Riemann sum. If the limit of the Riemann sum exists, then we say it's Riemann integral. But the question is, how do I partition this function, right? So first of all, this function is continuous, therefore it is Riemann integrable. But do I need an even partition? I say no. Here I use it says any partition is okay, right? Any partition is okay. So it's okay for me to use a special partition. So in this case, I'm going to use x a is less than a times r is less than a times r to the power of n, where r is b over a to the power of 1 over n. All right, so here I claim a to the power r to the power n is equal to b. The reason is because r to the power of n is equal to b over a. b over a times a is b indeed. So I have a uneven partition. Right? Uneven partition. So the next question I want to ask is that it says the choice of xi is random. Right? So it's okay for me to choose a special xi. It's okay. Right? I'm going to choose xi to be just the right edge of the small interval of my every small interval. So that is a times r to the power of I. Right? That is the right edge of each of my small interval. It's okay. So now the question is that as my partition gets dense enough, in other words, as my largest small interval gets small enough, p modulus gets small enough, is it equivalent for me to say that as n approaches infinity, does that mean my partition gets dense enough? Right, that's the question I want to ask. Because it may not be always true. It may not be always true. For example, if I use a partition I'm gonna choose the middle point, right? And fix the right hand side, fix it, right? Then I'm gonna partition on the left hand side. Very, very dense. In that case, as my left hand side partition gets more and more dense, but I'm keeping the right hand side fixed, right? Exactly half of b minus a. In that case, as n approaches infinity, right? As I have more and more small intervals, does that mean my partition gets dense enough? No. The reason is because I'm holding the right hand side interval fixed already. Always, the length is always half of b minus a. So in that case, overall, my partition is not dense enough. So not always true, but in this case, I say it's true. Why? Because, let me just make this claim that in this case, it's true as n approaches infinity, as I have more and more and more small intervals, my biggest interval of my small intervals can get small enough. The reason is because, right, here's my claim. As n approaches infinity, my p modulo will get small enough. The reason is because what's the width of my biggest small interval? It's easy for us to verify that. The width of my biggest small interval has to be exactly the last small interval. That is a times r to the power of n minus a times r to the power of n minus 1. Right? That is equal to a times r to the power of n minus 1 times r minus 1. Notice that r is bigger than 1, because b is bigger than a, bigger than 0, right? Because otherwise, if it's not the last interval, then we would have a times r to the power of I minus 1 times r minus 1. R minus 1 is fixed. The only thing that's changing is the power, right? I minus 1. So when I is very small, then my whole expression is very small. When does it reach the maximum? It's when the power reaches the maximum. It's when power is n minus 1, right? So that's why my width of my biggest interval has to be my last interval, right? So the question is, as n approaches infinity, as I have more and more and more intervals, small intervals, does my biggest interval really get small enough, right? Does this really tends towards 0? That's the question. Now, if I can just, again, replace I with my definition, right, with this one, see what happens. A times r, let me just plug into this expression, maybe more convenient, right? R is b over a to the power of 1 over n raised to the power of n, that is a times b over a, right? Minus plug into this, right? A times r to the power of r is equal to b over a, 1 over n, so n minus 1 over n, that's its power. So really, I have, in this case, I have b minus, what is this? Split up the power, right? Power becomes 1 minus 1 over n, split them up. And I have a times b over a to the power of 1. That is just b, right? Just b. Also, I have to times b over a to the power of minus 1 over n. That is, it's reciprocal. That is a over b raised to the power of 1 over n, right? A to the power of b. Yes. So in this case, as n approaches infinity, power approaches 0. right? Base is fixed. So the whole thing approaches just 1. 1 times b is b, b minus b. Really 0 as n approaches infinity. So really I've proven that as I have more and more small intervals, my biggest small interval can get small enough, right? So in other words, I can have a more and more dense partition in that case. So in this case, I can safely use the precise definition of the Riemann integral, right? Riemann sum, then take its limit. So now my Riemann integral a to b of just 1 over x dx is really equal to the limit. So instead of letting p modulo approach 0, it's equivalent for me to use n approaches infinity. It's safe now. And then we have the Riemann sum. I from 1 all the way up to n. F c I. According to the precise definition, the choice of c I, like I said, is random. But since it's random, then it's okay for me to, like I said, to choose a specific c I. I'm choosing the right edge of each small interval. That is this value, right? Plug this value into this function, right? 1 over x, that is x replaced with this one. That is 1 over a times r to the power of I, right? Then I have to multiply by delta xi. Delta xi is what? Delta xi is... So a times r to the power of I minus a times the power of... a times r to the power of I minus 1, right? A times r to the power of I minus a times r to the power of I minus 1. All right, then I let n approach infinity in this case. First, 1 over a times r to the power I times a times r to the power I. They just cancel out, first of all, right? I from 1 to n bracket, right? They just cancel out to be 1. And distribute this onto that. First of all, 1 over a. They just cancel out. And r, 1 over r to the power of I times r to the power of I minus 1. I have just minus 1 over power of I minus 1. Minus, I have r, just r at the bottom, right? Power is bigger than that power. Distribute this one onto the bottom. That's right. So I equals 1 r. So in this case, r is fixed, right? N is fixed, a b over a is fixed. So the inside my sum, there's no more I, right? Every term is equal to this term. How many terms do I have to add up? N many terms, right? So all I have to do is to work out that is equal to n times 1 minus 1 over r. That is, I just have to work out the limit of just n times 1 minus 1 over r, b over a over b to the power of 1 over n, right? Reciprocal, right? Just flip it. Now it looks like we have an undetermined form, right? We have positive infinity times 0, right? Undetermined type. So n approaches infinity. The power approaches 0, right? Base is fixed. The whole thing approaches 1. 1 minus 1, 0. Infinity times 0. Maybe we can use L'Hopital's rule, but we can't use L'Hopital's rule until we rewrite it a little bit. So I'm going to just rewrite it into, maybe let's move n down to the bottom, right? This time at the bottom I have 1 over n. Top I have 1 minus a over b raised to the power of 1 over n. Right, this time I have 0 over 0, undetermined type. Right, this time I can use maybe change 1 over n into x. So x approaches 0. X at the bottom, 1 minus a over b raised to the power of x. Right, still undetermined form, 0 over 0. This time we can use L'Hopital's rule. So just to derive derivative at the bottom, we have 1. Derivative at the top, we have, what is it? 1 is gone, right? Minus, copy down the minus. Exponential function, right? Base is fixed. So according to the formula, we should have log of just the base, right? A over b. And we have to multiply by itself. Multiply by function itself. Right? So essentially we would have, then we let x approach 0, right? Power approaches 0, base is fixed. The whole thing approaches just 1. 1 times this. So that is equal to minus log a over b, log b over a, right? Well, in fact, this limit is in fact well known. We don't necessarily need to use L'Hopital's rule anyway. Because remember, in the previous video, I've proven a well-known limit. Right? I've proven a well-known limit. The limit x approaches 0. X at the bottom, I have the base. Let's just use c to the power of x minus 1. 0 over 0 type. This is a well-known limit. Without using L'Hopital's rule, I've shown in the previous video that this actually approaches log a, log c. Right, this approaches log c. Because in this way, it's logically more sound. Otherwise, this way is technically right, but maybe it's not logically sound enough. Because when we use the L'Hopital's rule, when we derivative the top, right, how do we know that the derivative of exponential function is equal to this? Right? How do we know that? All right. At first, we used first principle, the precise definition of derivative. Right? So, but there's nothing wrong with this way. Perhaps just logically, it'll be logically more sound. Just maybe use this result as I proven in the previous video. Right? This without using L'Hopital's rule, I've shown in the previous video. So like I said, in the previous video, I've shown this limit is equal to log c without using L'Hopital's rule. It's because first I proved this limit. X approaches 0. X at the bottom. Top I have log 1 plus x. Again, it's a 0 over 0 type, right? X approaches 0, approaches 1, log 1 is 0. In that case, I've shown that the limit is equal to 1 because it can be written as 1 plus x raised to the power of 1 over x according to the logarithm rule, right? Is equal to 1 over x times log, and then put the 1 over x to the power, right? So the inside. So this is clearly exactly the definition of e, right? 1 plus x raised to the power 1 over x. X approaches 0. Power approaches infinity. Right, exactly e. Log e just 1. Log e just 1. Then in order to solve for this limit, I just let e to the power of x minus 1 equal to y. In that case, c to the x is equal to 1 plus y. Right. We take the logarithm on both sides. Right? In logarithm c, take down x, log c, log 1 plus y. Right? So take down the power, right? xc. So x is equal to log 1 plus y over log c. In that case, this limit is equal to c to the x minus 1, like I said, is y. Y over x, x is equal to this, right? Log 1 plus y, log c. Log c can be written at the top. Right, after we simplify everything. This time we let, when x approaches 0, which implies c to the x approaches 1, right? Left hand side approaches 0, implies y approaches 0. Right? Since y approaches 0, like I said, this limit is equal to 1 when x approaches 0. This time I have the reciprocal of log 1 plus y over y, reciprocal, right? The only difference is that here I have x, there I have y. Same thing, right? Still y over log 1 plus, still approaches 1. So still approach 1 times log c. Without using L'Hopital's rule, maybe this is logically more sound.